So first, let me apologize because this is the first time I'm speaking on this. So if I say something that's complete nonsense, please feel free to correct me. My other apology is that I'm not quite an analyst. So if this seems very applied, well, this is as close as I come to doing analysis. OK, so the idea that I want to talk about is what we call finite free probability. And first, I should probably mention what actual free probability is, just in case you haven't seen it. And free probability is a non-commutative version of classical probability. So actually, let me make a chart here. So over here, we have classical probability. And if you've never seen this before, the idea is essentially rather than taking a distribution, which you normally have here, and doing things to it, like adding it to other distributions, what you do is you take the distribution and you put it on as the eigenvalues of a matrix or some infinite dimensional operator. And then you can add those operators together. And the idea is, depending on what these rotations are, you get different things than what would happen over here. Okay, so over here you have an expectation. And here you have some tracial state, which is a trace function. Okay. And what is freeness? Freeness is the non-commutative version of what independence is over here. Okay, and so what is independence? Independence says that, well, so when you have two random variables and you want to add them together, say, you can't just do that because you need to know the joint distribution between them. But independence is sort of this special distribution which tells you that, a special joint distribution which says all you need to know is the original distributions, and then you can combine these two things and get another distribution without knowing any joint distributions. And freeness is going to be the same thing. It's going to be some way of taking a distribution of eigenvalues on a matrix and another distribution of eigenvalues on a matrix and doing some combination of those matrices and getting some new distribution where that distribution, all of the moments are only going to depend on the moments of the original ones.
Can I ask a question?
Yes?
What is the difference between the words freeness and freedom?
I don't know because I've never heard of freedom. So sometimes this is called free independence, and they use freeness for short. I've never seen the word freedom, so. OK, so over here, if you wanted to add two probability distributions together, let's say you have A, and you want to add it to B, two random variables, the way you sort of pedantically do it is you would first you would find the moment generating function, which is e to the x a. And then you would take the other moment generating function, e to the x b. And then you would form what's called the cumulant generating function by taking the log of these. And then you would add them together. And this would give you log of e to the x a plus b. OK? Yes. Thank you. And then if you wanted the distribution, you would go backwards. The same thing happens over here. You form what's called the non-commutative moment generating function, which is the integral of So if A has spectral distribution mu A, then what you form is this function here. This is the moment generating function. And then you form what's called the R transform. So this is G mu A of t. And then you form R mu A of t, which is G mu A t inverse minus 1 over t. And this minus 1 over t should not be overly mysterious. You should think of this as G mu 0 of t. So obviously, if you wanted to add 0 to something, you would want it to stay exactly the same.
You integrate with respect to x there?
Integrating with respect to t here. I'm sorry? So this is a function of, oh, I'm sorry. Yes. I'm sorry, thank you. So if you wanted to add something that had spectral distribution 0, you would want the thing that you added it to not to change. And so when you, well, let me show you. So the point is that you then define the additive convolution the same way by doing mu A plus mu B. And obviously, if you wanted to add a distribution that did nothing to the original one, you need to be adding 0 here. So this 1 over t is essentially turning, if you take this inverse of G mu 0, you need to, turn that into 0. So you're adding 0 to it. Okay.
I have a question. Is
Yes.
G mu 1 to 1 or what kind of inverse?
So it's not 1 to 1. So you can find many distributions that give the same moments. But typically, most of the computations you do, you really are just trying to understand what the distribution looks like in terms of its moments. So you can't really go backwards, but you can sort of characterize your distribution as best you can, in terms of moments at least.
But the inverse is not the reciprocal, it's just the inverse.
This inverse, so this is, right, so this is actually a power series compositional inverse. And it exists in some small ball around infinity. So you can use it as you can take it as a functional inverse. But the power series you're interested in is the one that's around infinity. Excuse me? Is the measure finite? Yeah, let me make it compact and just because that will reduce the chance that I say something that's wrong. Okay. And why would you study these things? Well, this thing was first introduced by Voiculescu in the 80s, and his reason for introducing it was to understand von Neumann algebras and various properties of them, in particular to show that various von Neumann algebras were different. But since then, and this was also recognized by Voiculescu, that a lot of things behave in this way. So for instance, if you take the what's called the Gaussian unitary ensemble, so this is the collection of the collection of matrices where all the entries are independently chosen to be Gaussians. What you get is that in the asymptotic limit, as the dimension gets big, this acts, the distribution of the eigenvalues of this thing is exactly the distribution of the eigenvalues of these free things. So if you added two of these together, it would be like adding adding two things together freely. Okay. So I've already mentioned sort of one of the reasons why this is sometimes difficult to work with. So this is a very good tool for trying to understand random matrices. The problem is that in order for things to act freely, you have to be in an infinite dimension, essentially. Because what ends up happening is that essentially if you have something that has finite dimension and it's free from something else, the only way for that to happen is if it's a multiple of the identity. So in order to get freeness, you have to be in infinite dimensions. And one example of that, so let me say what happens when you add. So over here, let me add, so x equals y is minus 1, 1, each with probability 1/2. Then what you get when you add these together independently is you get something that's minus 2, 0, or 2, with probability 1/4, 1/2, 1/4. If you take some operator A and put half of its eigenvalues to be minus 1, half of its eigenvalues to be 1, and then you freely add it to something else that looks the same, then what you get is a distribution that's first of all continuous and sort of looks like this between minus 2 and 2. Okay, so essentially as soon as you introduce this idea of freeness, like you are forced to be in continuous random variables, and so you're sort of forced to be in some infinite dimensions. And so my goal is to talk about what we call finite free probability, which is trying to extend this idea into the finite domain. And the reason for doing that is for applications such as Cadison-Singer and Ramanujan graphs and things like that, where you're actually trying to find or understand finite dimensional procedures, but they're acting sort of randomly in this free way. Yes?
I'm just curious by the graph. Is it the same as this semicircle?
So it's something like, yeah, it's like an arc sine law or something. I think if you add them together, like the central limit theorem eventually becomes the semicircle law. I don't think just the first two are, but.
The free sum.
Excuse me?
Yeah, you mean the free sum?
Free sum, yeah. Yeah. Because otherwise I can't even, otherwise this is sort of undefined, right? You have to know what the joint distribution is. Okay? All right. So let me start by talking about the Legendre transform. And the Legendre transform is a way of taking some function and doing sort of a point line duality on it. So here's my function, and what I want to know is, given some slope, how does this slope intersect this, essentially what point on this function has derivative which is this slope? And then the transform is actually what the y coordinate of this thing is. Now, there becomes this issue where you have something that looks like this. Obviously, there are two places where the same slope happens on that line. So what you do is you define it as sort of the largest one that happens. And to formalize this, you get what's called f star of y, which is the sup over x of xy minus f of x. And geometrically, this is what this is doing. Okay, so why do we care about this thing? Well, let's say that, you know, I was actually trying to solve this equation, and I said, well, let's let u be the arg sup of this thing. Then what does that mean? That means when I plug in u here into the derivative, it should be 0, right? So what that says is that u minus f prime, y minus f prime of u is 0, which in particular means that y equals f prime inverse of u. U is f prime inverse of y. And the important thing here is the inverse, right? So what ends up happening here sort of all of the combinatorial action is happening in the classical case because you're taking a log. Here, all of the combinatorial action is sort of taking place because you're taking an inverse. And so in order to understand what's happening here, we're going to try and understand the inverse. And the way of understanding the inverse is to use this transform. Okay? So essentially what happens, you start with f, you take the derivative, that gets you f prime. Then you have this inverse operation, which gets you f prime inverse, which is also f star prime. And then you can go to f star. Okay? And the last thing I will say before anything interesting happens is I'm going to use LP norms. FP and is what's called f infinity. And when f is continuous, mu is the Lebesgue measure, then f infinity is the sup norm. Okay? So the idea is just to change this definition of f star slightly. Well, not even change it. So I'm going to start with f star of y. And this is going to be the log of the exponential f star of y. Haven't done anything there. Then I'm going to plug in the definition here. This is sup for x, xy minus f of x. This is an increasing function, so I can bring the sup out here. Which is this as long as f is real. So for f real, so as long as this is a positive number, this ends up being positive, and so you don't have to worry about taking absolute values. So what you have is this. Excuse me? Oh, I'm sorry. This is absurd. e to the xy minus f of x. Is that better? At least correct? Okay. Okay. So, well, I erase this over here. If you remember what we were trying to do, we were trying to add together two things which were an inverse. And the inversion here sort of takes place after you've taken a derivative of the original function. So what I would like is to find some f so that f prime is my g mu a of x. And this is not hard because this, another way of writing this is to have phi of xi minus a inverse. And when you integrate this, you get that this is phi of the natural log of xi minus a. And this is also a well-studied sort of operator, which is related to what's called the Fugulady-Cadison determinant. And the Fugulady-Cadison. Excuse me?
What is this phi?
This phi is the expected value. Is so whatever this trace function is for your von Neumann algebra that you're on.
The both equality which is the array gives the same as.
Excuse me? Oh, I'm sorry. So this is supposed to be. Yes? Okay. Okay. So the Fugulady-Cadison determinant is delta of t, which is e to the phi of the natural log of t, where natural log of x is, phi natural log of x is the integral natural log of t d mu x of t, where x is the square root of x star x. And when x is positive semi-definite, well, yes? I'm sorry. A is a matrix, or let's say operator with spectral norm mu a, and mu a is what I'm trying to is, yes, some
Should it be ln of t, capital T there?
a spectral measure, I'm sorry. So yeah, so like a self-adjoint operator that has this as its.
Measure you mean the scalar measure? Multiplicity 1 or what?
So for an operator in a von Neumann algebra, it can be continuous, right? It could be. So it could also be a random matrix, for instance. So, but for fixed matrices, yes. When I have a finite dimensional matrix, I want to think of it as a uniform distribution on the eigenvalues. A distribution. So in the finite case, I'm really just saying it's a uniform distribution on the eigenvalues of the matrix. Okay? This is just the definition of what phi of. Yeah, sorry. This is just some operator. This is the definition. Yeah, sorry. This is also t.
So the last integral should be x.
Everything's t. So it's defined for von Neumann algebras. I'm only going to really use it in a finite dimensional case. Yes.
How is this phi is connected with A and with mu A?
So phi is given to you as part of the measure space. Phi is some trace. So you can think of it as the normalized trace on here, although you can extend it to other tracial measures. Okay, and then this is determined by your phi, and in our case, it's going to be the normalized trace. I mean, the problem is when you take the regular trace and you then take things in an infinite limit, the trace becomes infinite. So you have to define something which still remains finite, and that's what Fuguleti and Caddison did. Okay, so, right, what I wanted to say is that for T m by m matrix, del T is determinant of T to the 1 over m.
May I ask you, so
Yes.
this phi is a state.
A tracial unital state, I believe, yes.
On some von Neumann algebra.
Yes.
And this algebra is given from the very beginning.
It's given from the beginning, yes. That's your measure space, essentially.
Terminals can be general, not necessarily positive, but you assume T is some kind of.
Right, if T is positive semi-definite. Yeah, let me positive definite. That's right. Actually, this is true regardless, but. And in fact, this is really, so you can extend this to positive semi-definite, but I mean, it's easier when things are just positive definite. What is the punchline? The punchline is that I'm going to try f of x. So given some operator, I'm going to try f of x is minus the natural log of this thing. And what you get is that then f prime of x equals minus g mu a of x, which implies that f star prime of minus s is g mu a inverse of s. Sorry. Is, sorry. Minus partial derivative of s, natural log infinity norm. And that's using this over here.
And
S is sort of the dual variable. Sorry, this should be an S. Yes. Okay, so in other words, I can write this R transform as R mu A of S is minus partial over partial S, natural log of e to the minus xs natural logs, sorry. Right, this is just subtracting off what happens when the operator is 0. And remember, this is how I can define the convolution, the free convolution, right? This R mu A of S plus R mu B of S R mu A plus mu B of S. Okay?
Sorry, how do you obtain this formula with two infinity norms?
The two from this right here. So I can form F star using this. And then I just take the derivative of that. Right here, my f is, here f of x is the natural log of the Cadison-Fuglet determinant of delta I, of xi minus a.
There, in this formula, there is only one term which depends on x. Yeah? So how do you obtain the sum of two?
Here? You mean? Remember, this is, so this is G mu A inverse of S of minus S. I'm sorry. Shit. So this actually is G mu A inverse of S. Where the way I got that is by using this essentially to get my F star. And then by taking the derivative of F star, I get F star prime. And F star prime is the inverse of the derivative of F. And the derivative of F is this. So when I take the inverse, I get something that's a function of minus S. And then when I make a change of variables, it becomes this. Then R mu A is just G mu A subtracting off G mu 0, the way we talked about before. Right? Okay. So this is quote unquote 1 over S. But you'll see why we need it to not be just 1 over S. Okay? And the idea is that now I'm just going to do exactly the same thing, except I'm going to take away these infinity norms. I'm going to turn them into m norms for some m. Okay, so now I'm going to write R mu A m of S is minus partial over partial s, natural log of m norm plus m norm. Okay, that's just a definition. And I'm going to define a convolution exactly the same way. So I'm going to write R mu A m plus R mu B m is R mu A plus sub m mu B. Okay? And this is going to be my finite free convolution.
Sorry, you introduced m. Which values can it take?
Excuse me?
M where?
M is, yeah, but some number between 1 and infinity. So this is it's a real number, yeah. So this is an LP norm rather than an L infinity norm. Okay. And this is what I'm going to call my finite free convolution. Or at least my additive one. Okay. So in order to analyze this, I'm going to use what I call a U transform. And to get that, I need a lemma. So if S is a multiset, then there exists a T with size of S equals size of T such that natural log of the expected value x minus T natural log of x minus S, where the expected value means I'm taking each of the things in the multiset uniformly at random. Okay, and how do I see this? Well, if I take the exponentials of both sides, this becomes, oh, this should be, I'm sorry, I'm missing something. Oh, no, I'm not. This becomes, yes, I am. That's what I need, yeah. So this becomes expected value of x minus T to the T. Which is then some P of x, polynomial in x. And the idea is that you can find where the roots of P are the elements of S. So what you want is so I've given some degree D polynomial P. I want to find a random variable with support size D such that the expected value of x minus t to the d is this polynomial. And in order to do that, I need, if I multiply out this, or if I expand this function, I essentially get that each of the first d moments is equal to something over here. And I can turn I can turn constraints about moments into constraints about elementary symmetric polynomials. And then I can turn constraints about elementary symmetric polynomials into a solution of a given polynomial. And so at least over the complex numbers, this thing exists. So it's going to be the d different solutions of some polynomial that's formed by sort of interpreting the constraints of this polynomial being equal to this polynomial as some constraints.
So we will not quite understand. S is a multiset of what? Capital T is also a multiset of?
So like complex numbers. This might actually be wrong. This statement here. What I want is to say that the expected value of x minus t to the d is equal to product of x minus si, where I equals 1 to d. So s is the roots of some polynomial. I can change it so that the roots of this polynomial are the expected value of x minus t to the d. And t has the same cardinality as s does.
What is the random variable here?
It's the elements of the, so I'm picking them randomly, uniformly at random from the set. So this is 1 over d, sum over I, x minus ti to the d. So this is just really a notational convenience. The point is that when this, so let's say that A is m by m, rather than infinite dimensional, it's a matrix. And I form this R mu A of S. What ends up happening is that this is the minus partial over partial s natural log of the expected value of e to the minus ms, let's call this y sub a, plus O of s to the m plus 1, where ya is the U transform of the eigenvalues of A. Okay, so the purpose of the of this U transform is because it makes, doing calculations on these R mu's much easier. When M is when A is an M by M matrix, then what you get is that this R mu becomes the expected value of e to the minus ms ya, where ya is the U transform of the eigenvalues of A. And then this looks exactly like the moment generating function of a classical random variable, at least up to the first m moments. And so essentially this is exactly, so you can see how that ends up becoming this, right? Because I'm just adding together two things and getting this. So
Transform is defined in the level.
The U transform is right, whatever this multiset is that, yeah, so T, I'm sorry. So T is the U transform of S. So what you get is that if A is a m by m matrix, and B is an m by m matrix, then expected value of x minus y a plus mb is so you can actually, if you have these U transforms, they do the M convolution up here the same way that you would just add two things together. Okay? So, extremely long story short. So actually, if you want to ignore the entire thing that I've said so far, that's probably okay. The whole point was just to get to this statement right here and to do it in a way which connects to free probability. But what essentially we have now is an operation on polynomials. Right? So let P of x be where A is m by m, B is m by m, Q of x is determinant of xi minus b. Then I can write P, let me abuse notation and write this again, is determinant of xi plus, minus and I have a formula for it. So if sum over I, so P of x, sum over I, x to the m minus I, minus 1 to the I, pi, then this is sum over I plus j less than or equal to m, should be m, minus 1 to the I plus j, m minus I factorial, m minus j factorial, qj. Okay, like 30 more seconds? 3 minutes? Okay. So I now have this way of taking two polynomials and forming a new polynomial. The way that I got them was from turning this free probability into this operation. The good part about this operation is that unlike in the infinite case, where I had to take the moment generating function, then take the R transform, and then add the R transforms, and then undo the R transform into another moment generating function. Here, if I know the distribution of eigenvalues on each of A and B, I can just spit out directly this polynomial, which has eigenvalues which are the eigenvalues of A with my M convolution of B. And the idea is to try to emulate what's happening in free probability, and this is accentuated by the fact that this is actually integral over O in the Q in O to the M, determinant of so if I took a random polynomial where I added these two together, but I did it with a unitary transform, a random unitary transform, this is exactly what I would get. Okay, so this is some way of combining two quote-unquote random matrices and getting a new one. And it is supposed to emulate what's happening in free probability. Next time I will talk about this some more. The interesting thing is that when these two are Hermitian matrices, that means that these two polynomials are real-rooted, and there is a theorem in polynomial geometry which tells you that if you do this operation to two real-rooted polynomials, you get a third real-rooted polynomial, which is a non-trivial statement. But it means that this thing sort of makes sense as a way of understanding at least Hermitian matrices and the way that they add together randomly. So I'll continue next time.